Okay, welcome back. It is now part 2 for the introduction to linear algebra, and now, right, we will go on a bit deeper as to how matrices are like numbers, right? Numbers can be manipulated. They can be added together, they can be subtracted, they can be multiplied, they can be divided by each other. In some cases, spoiler alert, they can be raised to other numbers, right? They can be exponentiated. Is that the case for matrices? Well, yeah, kind of, maybe, right? We'll talk about the most basic operation that we know of, which is matrix addition. Right? For matrix addition, yes, you can add two matrices together, and the biggest rule, the most obvious rule as well, is that they need to have the same size. For you to add two matrices together, they need to have the same size. Anything else and you will result in a does not exist, right? Or, well, you can't answer it basically. So say for example, we have here matrix P, which I don't know. Let's say for example has 1, 2, 3, 4, 5, 6, right? And say for example, we will have Q, which we will have I don't know, 1, 3, 5, 7, 11, and then 13, something like this. So very clearly, right, P is a 2 by 3 matrix. Q, on the other hand, is a 3 by 2 matrix, right? So we can see in here, right, that matrix P has 2 rows and 3 columns, right? And then your Q has 3 rows and 2 columns. So in this case, sadly, P plus Q is not available to us, right? On the other hand, though, if say for example you were to transpose Q, you would have something, right? Let's try and see what's going to happen. We will have 1, 2, 3, 4, 5, 6. What I will get a hold of is the line of symmetry for your Q. In this case, it starts from our first element, and then you do this, and then of course you're going to flip it, right? And so what you expect is instead of a 3 by 2, you get a 2 by 3, which in this case is 1, 7 is retained right here. 3 will go on the other side, and then 5, and then 11, and then 13. And so that means that your P plus the transpose of Q will give you, just look at the elements themselves. This is going to be an element-wise operation. 1 plus 1 is 2. 2 plus 5 is 7. 3 plus 11 is 14. 4 plus 3 is 7. 5 plus 7 is 12. 6 plus 13 is 19. That is how you solve for your P plus the transpose of Q. And now I challenge you, what about the transpose of P plus Q, right? What will that equal to? Okay, so that is your matrix addition. Hopefully very understandable naman so far. And now we will go on to scalar multiplication. What do we mean scalar multiplication? In the sense now, because we have introduced matrices as like numbers, you're going to expect that you are going to encounter a scalar, or basically just a normal number, with you at some point in time, right? And so, well, what is scalar multiplication going to do? Well, it is another kind of element-wise operation. Say, for example, we still have our values of P and Q in here. What if I were to ask myself, okay, what is 3P? Right? Your 3P is just 3 times whatever you've seen in here. 1, 2, 3, 4, 5, 6. And it's an element-wise thing. 3 times 1 is 3. 3 times 2 is 6. 9, 12, 15, 18. And so, you can create stuff like this. I don't know. You can create stuff like 4P minus 2Q transpose. Okay? You can create something like this, right? What would be the value to that, right? We would have, that would be equal to 4 times P. So this is 1, 2, 3, 4, 5, 6. And then your minus 2 times your Q transpose, which is this thing. 1, 3, 5, 7, 11, and 13. Let's just expand. We will get 4, 8, 12, 16, 20, 24. Right? And then plus, right? We will multiply -2 everywhere. -2, -6, -10, -14, -22, and -26. And now again, an element-wise kind of operation. 4 minus 2, 2. 8 minus 10, -2. 12 minus 22, -10. 16 minus 6 is 10. 20 minus 14 is 6. 24 minus 26 is -2. That is our value of 4p minus 2 times the transpose of q. Right? So that is how scalar multiplication works. And now, a couple of things to remember, or rather to think about when we're dealing with matrix addition, now that we have introduced our scalar multiplication. There are a couple of properties that are available for us. In this case, right, the commutative law applies. You might tell yourself, what is the commutative law? The commutative law, when we're talking about numbers, basically states that a plus b, right? A plus b is equal to b plus a. This is our way of telling ourselves that, yay, this thing, right, even if it's a number or a matrix, order does not matter when it comes to addition, right? So even if it's just a number or a matrix, this is still going to hold as true, right? Okay. Besides that, we will have the associative law, right? Associative, maybe, right? The thing about a plus b plus c, say for example, we have a plus b plus c. The hard part to think about this is that what am I going to do first, right? Will I add a and b first and then c? Or say for example, what if I just add b and c first, b and c first, and add that to a? The thing about the associative law is that if it's a number, it doesn't matter. Right? The order of operations in this case does not matter so long as it's all what do you call this? It's all same, right? It's all addition. So in this case, it is also true for matrices, right? Either you add a and b first and add that to c, or you can add b and c first and then add that to a. C. So there you go. The associative law still applies. And say for example, you have here a scalar. Say for example, you have k, and I will denote it in white because it is not a matrix, right? If say for example, you have a and b together, right? A and b together, what you can do is just say, oh, it's k times a plus k times b. I'm here to say that that also still applies for matrices, right? For matrices, ka plus b is equal to k times a plus k times b. Okay, so those rules apply still, right? Those rules apply still. Now, we're going to get into the hard part, right? The determinant. Okay, the determinant in this case, you know what? Wait a second. How long has it been? It has been 9 minutes. Okay, so we can go a little bit more into the determinant because this is not just the determinant itself. It will have to go into basically everything else in here. But even before that, I've completely forgotten to mention that we will have matrix multiplication. This, I suppose, is the hardest bit in this section, or well, it's not the hardest, it's just the most tedious, right? And matrix multiplication is the representation of multiplication, well, in the matrix world. How are you going to multiply two matrices? Well, just like with matrix addition, there is an interesting thing to think about when it comes to the size of the matrices. in this case, the size of the matrices do not have to be the same. Most likely that will not work, right? Say for example, if in this case your P and your Q are 2 by 3 and 3 by 2 respectively, you can actually multiply, right? You can actually multiply. However, if you multiply P to itself, a 2 by 3 by a 2 by 3, you will not get anywhere, right? That is not going to give you a correct answer. So you know what? Let's just cap it off at matrix multiplication. What matrix multiplication will do is, oh boy, how am I going to say this out loud? This is kind of like a dot product, right? So if you remember what a dot product is, it's a kind of an element-wise multiplication and then addition, right? So if you don't remember what a dot product is, that's completely fine. Say for example, we have unit vectors, or we have two vectors right here. Say for example, we have, what are two good names? Oh, just like R and S, right? R and S, right? The thing with R is, say for example, it is 3 I hat plus 4 J hat minus 2 K hat. And then your S is, say for example, 5 I hat minus J hat, right? And then plus 4 K hat. When you're going to put these together, right, your R and your S, and then you're gonna have a dot product. I feel like we'll just stop here for now, right? We can multiply each, right? We can multiply each vector, each corresponding vector. In this case, 3 times 5 is 15, 4 times -1 is -4, and -2 times 4 is -8. So 15 minus 4 minus 8, that gives us a value of 3. And so the thing is this: when you're creating matrix multiplication, or when you are doing a matrix multiplication, you are doing a bunch of these element-wise multiplications, and then you add them up. So I feel like this is not the best way to tell you guys about it. Suppose the best way is to just try it out for ourselves. We have here, I'm running out of letters in the alphabet. P, Q, R, S, T, U, V, W, X, Y, Z. You know what? Let's just go with a very classic X and then Y. -2, 2, 5, 3, 0, 1. And then, say for example, we will have Y, which is in this case 8. Oh boy, 8, -2, 5, 0, 0, 3. Yeah, there you go. And now the thing about this is that X, to be clear, right, X is going to be 2 rows, 3 columns. Y, on the other hand, is going to have 3 rows, right, and then 2 columns, right? So we have 3 times 2. Thing about this is that you can only perform matrix multiplication if, right, say for example, you want to get the value of X times Y, you're going to have to look at their sizes. X is a 2 by 3, Y is a 3 by 2. The sticking point here is this: matrix multiplication is only possible if these middle two numbers are the same. And you will expect the result, excuse me, Cole. You will expect the result, say for example, the result, let's just call that P for product. The result will be, if you remove this number, this is the result. The resulting size, right, we can already know is that your P is a 2 by 2 matrix. And so how are we going to do something like this? Well, what we're going to do is -2, 2, and 5, and then 3, 0, and 1. On the other hand, we will have 8, -2, 5, 0, 0, 3. Now, we expect that this thing is 2 by 2. So let's lay the groundwork. This is now your 2 by 2 matrix. You might say to yourself, wait a second, this is too large. I think this is actually a bit too small, right? What we will do is we will focus on rows and columns. This is not switchable, huh? I'm spoiling one property right now. You cannot switch the order. The commutative law for this case does not exist. Okay, so if this is going to be xy, that's fine. Yx is going to solve or is going to yield a completely different value, so we should be very careful. Okay, so for the first, right, so for the first what do you call this, first matrix, we will only look at the rows, and for the second matrix, we will only look at the columns. Okay, so what's going to happen, we will pick a row, so this is row 1 and this is column 1. If we remember, in our 2x2 graph, this is where row 1 column 1 is. So you might say to yourself, okay, so clearly this value has something to do with the things that you've encircled. Yes, we're gonna have to do a dot product of these two kind of vectors, if we want to think about it that way. -2 times 8 is -16, right? Positive 2 times 5 is +10, and then 5 times 0 is 0. So -16 plus 10 plus 0, your value in here is -6. Okay, very interesting. And then now -6. We will now have second row, first column. Second row, first column, it now corresponds to this. Okay, I'll just do this, right? 3 times 8 is 24. 24 plus 0 times 5 is 0. 1 times 0 is 0. So this is just going to be 24. 24. And then we will have first row, second column. We will now have -2 times -2 is positive 4. 2 times 0 is 0. 5 times 3 is 15. 4 plus 15 will give us 19. And then, right, we will have second row, second column. Right? 3 times -2 is -6. Plus 0 times 0 is just 0. 1 times 3 is 3. So -6 plus 3, we will get -3. That is your value for P. What is completely different, however, is your Yx. In this case, now we have switched things together. We have a 3x2 matrix and a 2x3 matrix, and we can see that both of them are going to have a 2 in the middle number. So if we're going to cross that out, we can say to ourselves, oh, Q pala in here is a 3x3 matrix. How does that work? Well, you've seen how it works. We'll just try and look at it a different way. This is your X. This is your Y, pala rather. And your X is -2, 2, and 5, 3, 0, and 1. And again, we can recognize now, okay, the answer to this thing needs to be a 3x3 matrix, right? But then again, right, what we're going to have to do is just label and basically index everything in here. This is row 1, column 1. So we will do what we do best. This one for the rows, this one for the columns, and then we fill out this. First row, first column, 8 times -2, -16. And then -2 times 3 is -6. -6 times 16 minus 6 will give you -22. And we keep going. 5 times 2 is 10. 0 times 0 is 0. So this will be second row, second column. So 10. And then last row, last column, 0 times 5 plus 3 times 1. So that is just 3. Okay, and you can rest and you can fill in the rest, hopefully, right? First, second, right? First row, second column, 8 times 2, 16, -2 times 0 is 0. So this is 16, right? And then first row, last column, 8 times 5 is 40. -2 times 1 is -2. 40 minus 2 is 38. Okay, so second row, first column, 5 times -2 is -10. And then 0 times 3 is 0, so -10. And then we will have second row, third column, 5 times 5, 25. 0 plus 1 is 0, so this should be 25. And then we will have last row, first panel. 0 times -2 is 0. 3 times 3 is 9 is, that means that will just be 9. This one and then this one. We will have 0 times 2 is 0. 3 times 0 is 0. So this will be 0. So as you can see in here, a wide range of difference, right? Just because you switch the order from x times y to y times x. So we need to be extra mega careful when we're looking at matrix multiplications. So now we've passed 20 minutes, right? Afterwards, in part 3, I will let you guys know what the properties are of these matrices, right? It is very clear that at this point, right, the commutative property does not hold, right? So just because it's true for some matrices, that does not mean that it is true for everybody. Again, right? If you just have P and Q transpose and you try and have them multiply, that's not going to work. Okay, that's not going to give you an answer. But that is for later. For now, we will. I'm glad to have taught you guys matrix multiplication. Okay, see you in the next video. Thank you very much.